All right, let's take a look at this kind of review assignment there to get the tools that we're going to need for being successful in this unit. So, identify the locations of the vertical and horizontal asymptotes in this. Well, that looks like a transformation of our reciprocal function. So, I'm going to do this with an arrow diagram. We start with the x, we subtract 3, and then we flip that over. There's the parent function happening right there. And then we multiply that by 2 and add 5. And normally in this, if I wanted to know where the horizontal asymptote was, that had to do with the in behavior. So as it goes to negative infinity, as it goes to positive infinity. And the vertical asymptote usually happens where the 0 is, because that does division by 0. It creates the vertical asymptote that way. Okay. Well, if I add 3 coming back this direction, still left hand in behavior description and right hand in behavior description, and 0 plus 3 is 3, and so 3 is where the vertical asymptote is at x equals 3. So x equals 3 is the vertical asymptote. And my horizontal asymptotes over here, normally this approaches 0 on these. If I double that, it's still 0. I add 5 and I get to 5. So my horizontal asymptote is at y equals 5. That's the in behavior description there. So y equals 5 is the horizontal asymptote. Okay. All right, what is the degree of this polynomial? Well, the degree of the individual terms, this has degree 0 because it has no variable in it at all. This has a variable of x with to the third power, so that term is degree 3. This has no variable, so it's also degree 0. This has an implied 1 in the exponent, so that has degree 1. And this has degree 2. And the biggest one in the list is a 3, so this is a degree 3 polynomial, which we would have also called a cubic. Okay, but that's the degree of that one. Solve this quadratic equation. Well, to solve quadratics, we need to make them say equal 0, so that's going to be 6x squared minus 2x minus 20 is equal to 0. I notice those are all even, so I can pull out a greatest common factor of 2. So I get 2 times 3x squared minus x minus 10 is equal to 0. And I've got 2, obviously, can't make it 0, but I could try to factor that part. So let's try the factoring. We'll get a 3x squared up here, and a minus 10. 3 times negative 10 is negative 30. So we need numbers that multiply to negative 30 and add to give me negative 1. Sounds like a negative 6 and a positive 5. So one of these will get a negative 6x, the other will get a 5x. This, I can factor a 3x out of there, which would leave this as an x. That as a minus 2. That as a plus 5, and the 5 times negative 2 makes a negative 10. So this factors to 2 times 3x plus 5, and x minus 2 equals 0. And the zero product property says that can only happen if the 3x plus 5 equals 0, or the x minus 2 is equal to 0. That would be 3x equals negative 5, and x equals negative 5/3. Or x equals 2. So those are my solutions to that quadratic. Okay. All right, subtracting fractions, we need a common denominator. 15 is a 5 and a 3. 21 is a 3 and a 7, so my new denominator needs to have a 5 and a 3 and a 7. Fix my numerators. This had the 5 and 3, but not the 7, so I'm going to need to multiply by the 7 on top there. So I'll show more steps here. And then there's subtraction. This had the 3 and the 7 that it needed, but didn't have the 5, so I need to multiply by 5. 8 times 5. So this is a 49 minus 40 divided by 15 times 7, or 21 times 5. 21 times 10 would be 210, so 105 is the denominator there, and that's 9 over 105. Those are both divisible by 3. So that's 3 over, and that goes in there 35 times. So the answer here is 3/35. So finding the common denominator, doing the subtraction, finding that can be reduced after that. All right, dividing with fractions. When you divide with fractions, we change it into a multiplication problem. So the 77 over 30 stays as it is, but we change that to a 12 over 44. And these are some big numbers to multiply together until we realize that there is some simplifying that we could do. These are both even here. 12/14 certainly is 6/7. 77 over 7 is 11 over 1. 6 over 30 here can be a 1 over 5. And so what I have left in the numerator is an 11, and then the denominator is a 5. So the answer is 11/5. Doing this simplifying early here saves me simplifying later. Okay. A lot easier than adding and subtracting than multiplying and dividing. All right, based on fundamental theorem of algebra, what is the maximum number of possible solutions to this equation? This determines that this is degree 4. And the fundamental theorem of algebra said that the degree of a polynomial determines the number of possible solutions that it could have. And so since it has degree 4, therefore there could be as many as 4 solutions. Doesn't guarantee that they are, and those solutions, some of them could be repeated solutions. That's our idea of multiplicity, and some of them might be imaginary or complex solutions. All right, let's see, last problem. Based on what I see in the graph at the right, what is the equation for g of x? Well, fundamental theorem tells me that since this hits, this is a -5 here, and that's a 5. Those are a little small to see there. I don't really care what the numbers are on the y-axis, but this hits here at -2, 0, and this hits out here at 3, 0. And the way this one crosses is just like a straight line, so this has just multiplicity 1, but because this comes up and touches, it has an even multiplicity. So the simplest version of this equation would say that if I factored it, I would have gotten an x plus 2. That's what made it cross the x-axis there. And multiplicity 2 would have meant that it was squared. This one, to make it cross out there, I would need an x minus 3. And it goes straight through, so that's a multiplicity of 1. So this is the equation that should work there. The multiplicity, since it was even, for x equals -2 meant an even power on x plus 2. If that doesn't make a lot of sense to you, then you need to talk to me in class, because it should make just an awful lot of sense. All right.